Hello, this lecture will cover pages 196 through 202 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on counters and registers, Part A, Asynchronous and Synchronous Counters. We're going to start out on page 196. Counters and registers. We'll discuss two types of counters in the next couple lectures. Asynchronous or ripple counters and synchronous or parallel counters. Another name for asynchronous counters, as you already know, is ripple counters, and another name for synchronous counters is parallel counters. We've already discussed asynchronous ripple counters in previous lectures. As a review, I want you to see lecture notes 162 through 164 and video lecture 5C at the 11-minute mark. About 11 minutes in, you'll see that it discusses asynchronous ripple counters. In the textbook, 376 through 382 or 410 through 416, whatever edition you're using. See examples 7.2 in the textbook and 7.3 in the textbook. These are really good examples, both of them. So if you have a minute to take a look at them, I would take a look. Find this example 7.2. Looks like that. And find example 7.3. Looks like that. Make sure you understand the examples. On page 197, we're going to talk about synchronous parallel counters. We've never discussed these yet. These are new. In the textbook, you can look at page 382 or 416, depending upon your edition. Let's first look at a synchronous parallel mod 16 counter with look-ahead carry. It's a 4-bit counter. It's a mod 16 counter, which is a 4-bit counter, and it looks like this. And I want you to notice the inclusion of two gates. There's a 2-input AND gate here, which is taking these two inputs here to look ahead to get a count. You'll see that in a minute. And a 3-input, which is taking the outputs of these three. And then if you had to have another one, if you went to a 5-bit counter, you'd have to have a 4-input AND gate to look ahead to pass on to the next state. We're going to first of all mention the fact that the way you can tell that you're looking at a synchronous or a parallel counter is that the clock goes to every single flip-flop in parallel at the same time. That's why it's called a parallel counter. The clock feeds every single clock on the flip-flop. A ripple counter just went to the first one. Remember? And then the LSB. Then the LSB output was the clock of the next one, and the clock of that gate was the clock of the next one. The clock rippled through. That's why they were so slow. If you look back at the timing diagrams that we covered with the asynchronous counter, you'll see that if the clock period got smaller and smaller and smaller, you might not be able to get all the flip-flops reset, because it takes time for that clock action to ripple through all the different flip-flops. So it had a limitation in speed, and we talked about that equation. You should be familiar with it. But here, these counters are a lot faster because of this look-ahead carry. I'm going to explain to you how that works. If you take a look here, we're going to stay on the page, but I'm going to get my transparency so I can write on it a little bit. I want you to notice, first of all, you're looking, like I said, you're looking at a synchronous counter because the clock goes to every single flip-flop. If you're the first flip-flop here, the LSB is a toggle. It's set up for a toggle because the LSB toggles every time. I don't know if you noticed that in your all these different states, binary numbers. It toggles every single time from an even number to an odd number to an even number to an odd number and so forth. And then every 2 times, the next one. And then every 4 times, the next one. Then every 8 times, the next one toggles. So these other flip-flops in a synchronous counter, they toggle, but they only toggle whenever the J and the K is set up to a 1. So if you take a look here, the first flip-flop will toggle right away from a 0 to a 1, assuming they're all zeros to start out with. And then the first flip-flop toggles the output to a 1. Okay. This 1 gets fed on the J and K, so when the next clock comes, it toggles B. Because a 1 was set up, this 1 here was set up here. So it toggles this and this back to this to a 1, and this gets toggles back to a 0. Now you have a 0 and a 1. This output's still 0 here. If you take a look, the output on C is 0. But you have a 1 on B and you have a 0 on A. So this 0 on A is not going to toggle this flip-flop. It's going to stay at a 1. The LSB is going to toggle, so that's how you get to count 3. Notice gate 1 and gate 2 didn't come into play yet. But now we have this look-ahead carry in gate 1. We have a 3 condition. We have a 1 here on A, and we have a 1 here on B. So between clock pulses, and that's what's important here, all this happens between clock pulses, so it's set up with this look-ahead carry. There's a 1 on A and a 1 on B, and that's your count of 3, and that 1 and 1 is set ahead through that gate to a 1 on the J and K of this third flip-flop. So when the clock comes, this toggles to a 1 very, very fast, because this 3 condition, this 1 and a 1, gets set up between clock pulses, and that toggles you to a 4, a 1, 0, 0. This toggles back to a 0, this toggles back to a 0, and because the 1 is set up on the J and the K, flip-flop C toggles to a 1, and there's your count of 4. And then gate 2 comes into play on your look-ahead for 7 to 8. Notice from 7 to 8, you have a 1 on A, you have a 1 on B, and you have a 1 on C. So you get your 1, 1, 1, that's your 7. That's set up between clock pulses. When the clock comes, toggles back to a 0, toggles back to a 0, toggles back to a 0. The 1 and the 1 was set up here on the J and the K for D, and it toggles to a 1, so you go to your 8th state. You go from 7 to a count of 8 because of the look ahead. This allows for very fast speed compared to the ripple counters. Matter of fact, on page 198, you'll see for parallel counters, the period of the clock has to be greater or equal to the propagation time of one flip-flop plus the propagation time of one gate. Makes no difference how many flip-flops you have, because you always just have one propagation delay for one flip-flop, because these are toggling. These may toggle. You just have to account for one of these toggling or all of them toggling, and one propagation time of a gate, because this is your setup time, the time it takes to set up these gates, to get these inputs ready. So this is your equation for maximum frequency for a parallel counter. It's 1 over the minimum propagation time allowed, minimum period allowed, and 1 over the minimum period gives you the maximum frequency. And that minimum period is propagation time of one flip-flop plus the propagation time of one gate. That's a very important equation. And I want you to compare that equation to the propagation time of in your book here. If you would have read it, you would have seen for ripple counters, we have propagation delay in ripple counters can be a problem. And they explain that problem over here. If you look at in the book, there's no problem here because the clock speed is slow enough. But if you increase the clock and the period gets smaller, you may miss a state because you're not allowing for enough time for all the flip-flop rippling action to take place. That's why ripple counters are a lot slower. But this is what I was getting at. The maximum frequency for a ripple counter is equal to 1 over the number of flip-flops times the propagation time of one flip-flop. It's dependent upon the number of flip-flops because of the ripple action. That's an equation we already discussed. Compare that equation for a asynchronous or a ripple counter to a synchronous or parallel counter equation. Two different equations. So here's example 1. I want you to look over example 1 very carefully. And I want you to tell me what the maximum frequency for a ripple counter design would be. It would be 2.5 megahertz. And for a parallel counter design, it would be 33 megahertz. Notice that the parallel counter is much faster than the ripple counter. But you know what? If you don't need the speed, ripple counters are great because they're simple. They're easy to build. Notice how much faster the parallel counter would be. Look at the circuits and your lecture notes, and I want you to tell me why. Based on everything I told you now, you should realize that parallel counters are a lot faster because they have the look-ahead gates and the clock goes to every flip-flop at the same time. Advantages of synchronous counters over asynchronous counters. If you take a look in your textbook, not a lot of reading here, but I think it's something that you want to look at. You're going to be tested on this. Advantages of synchronous counters over asynchronous counters. Make sure you understand this. I mean, asynchronous counters do have an advantage over synchronous counters. They're easy to build and they're simple. I mean, they mention it down here. Of course, the circuitry of the synchronous counter is more complex than that of the asynchronous counter. They mention that in passing. There's nothing wrong with ripple counters if you don't need the speed. And example 7.4, in your textbook, whatever page it's on, make sure you take a look at example 7.4. You're going to have problems on the quizzes or the exams similar to these. On page 199, example 2, I actually went in and looked at the spec sheets of a LS74LS112, they're JK flip-flops, and 74LS11s, they're AND gates. I would encourage you to go ahead and get your specs out, or look at the link I have posted in Canvas under links, and just call up the spec sheet and get the propagation delays. Use maximum propagation delays here, but and see if you get the same frequency I do, 22.7 megahertz. That's the answer. Here's another example. Again, I'm using LS112s and LS11s. And I want you to see if you can get 22.7 megahertz. Notice these are the same frequency. This is a 4-bit parallel counter. This is a 6-bit parallel counter. And it's the same answer. Can you explain your answers? Pretty easy. If you looked over the advantages of synchronous counters over asynchronous counters in the book there, I think then you look at your maximum frequency equation, I think you'll see that the number of flip-flops makes no difference in parallel counters. You should understand that. On page 200, we decoded ripple counters. We're going to decode synchronous counters now too. Counters with mod numbers less than 2 to the n. I mean, if you're running a counter, you know, a mod 2 or a mod 4 or mod 8 or a mod 16, a mod 32 or mod 64, they're free. If you want those counters, they're all free running counters. You just let them run free run, and when they get to the maximum count of all ones, they'll go back to all zeros, and you know, they're free running counters. You don't have to decode those. But what if you need a mod 28, or you need a mod 21, or you need a mod 18, or even a mod 60, for instance, or a mod 12, a mod 10, or a mod 5? These fall into the categories of mod numbers less than 2 to the n. You have to decode those. And you already know how to do this, but I want to make sure it's crystal clear you know how to do it. Here we have a 5-bit counter output. This is the output of a 5-bit counter. You could design a 5-bit counter, either a 5-bit parallel counter or a 5-bit ripple counter. Just look at your circuits and build it. And the LSB is the output of the LSB. That flip-flop will be A, and then B, and then C, and D, and then E. E is the most significant bit. How would you decode the following mod counters to produce a mod 28 or a mod 21 or a mod 12 or a mod 10 or a mod 5? How would you decode the 28th state? And at 28, you clear. So 28 is the 0 state. It becomes that 0 state. So shut off the video, turn off the video, or pause it, and I want you to go ahead and show me these inputs here. If you did it correctly, and I hope you do, because you have to know how to do this, and you should understand it. There's your answers. There's your decodes to get a mod 28, or to get a mod 21, or to get a mod 12, or to get a mod 10, or get a mod 5. There's 5 examples. And this goes to the clear of all flip-flops, the asynchronous clear of all the flip-flops. This would go to the asynchronous clear of all the flip-flops. On page 201, we're going to look at a mod 6 parallel counter with a display now. And I want you to notice here, let's take a look at this. This is a mod 6 parallel counter with a display. Notice the display is just LEDs, light emitting diodes. Here's one output. There's your A output. Here's your B output. I drew it in here. And here's your C output. Here's your A, here's your B, and here's your C. There's your 3 bits. And I want you to notice they're driving these LEDs with low assertion levels. We already discussed that. That's very important for engineers to understand. You're not going to get enough source current out of here to drive these LEDs. So what they do is they're taking these. Just take a look at one output. They're all the same. Let's take a look at C. When C goes high, they run it through an inverter to get a low assertion level here. When C goes high, this point will go low. When this point goes low, what you're doing in the totem pole output of this inverter is you're saturating that bottom transistor and you're pulling this to ground. When you're pulling this to ground, you're forward biasing this diode. And you won't have any trouble syncing that enough current there to get that LED to light up. You'll be pushing to get 20 milliamps, obviously, but I'll tell you, even 2 milliamps, 3 milliamps, 4, 5, 6, 10 milliamps, anything above 2 milliamps, you're going to see an LED light up. And you know you can sync 16 milliamps here. We talked about that in the previous lecture. But anyhow, notice we have our look-aheads here. When you go from 3 to 4, this guy will help us here. Because you already have a 1 set up here and you have a 1 set up here. There's 3. Between clock pulses, you'll have a 1, 1. And with the propagation time, you'll have which is built into your maximum frequency equation. You have a 1 and a 1 here. So in between clocks, that got set up. So you had a 1, 1, and I put a 1 here. So you went from a 3 to a 4 with no problem at all. But when you get to 6, when C and B are both 1s, that's decoded, and it clears every one of these. So the state transition diagram here is 0, 1, 2, 3, 4, 5, and 5 takes you back to 0. Every circle represents a state, and every arrow represents a clock. And here's your mod 6 counter. Notice if you're in state 6, for whatever reason, if you get into state 6 up here, or if you get into state 7 up here, that's going to put a 1 and a 1 on C and B, either one. And as soon as you get a 1 on B and a 1 on C, it takes you right back to state 0. So these would be temporary states. If you'd ever turn this circuit on, it would come up in any one of these states. It would put you right back to state 0. That's why they call these temporary states. That decode would put you right back to 0, and you'd count. I want to look at this a little more closer to finish up the lecture, and I want you to notice something here. On page 202, we took away the display. This is the same mod 6 counter, but I want you to notice here when you get to a 6, a 1 here and a 1 here, that 1 here, and this is the 6th state right here. When you get to a 6, 0, 1, 1, so you have a 1 here and a 1 here, that 1 and that 1 here and here will cause the output to go low just for a nanoseconds. And that'll clear these flip-flops and it'll put it back to 0, 0, 0. I mean, you're really going to hit the 6th state. I mean, in actuality, and this is what I want you to try to understand here, you're going to go up to the 5th state, and you really have to proceed into the 6th state before it gets decoded back to 0. Now, most of the time, that's not going to be a problem. I mean, normally it's going to count 0 through 5, and you're going to go right back to 0 because it doesn't spend any time here, and it's not going to interrupt. It's not going to harm your application. But in some cases, that little glitch, that little temporary glitch into state 6 could cause a problem. I wanted to point that out. In some high-speed electronic digital circuits, that could be an issue, and you'd have to take care of it. Okay. So, but in our applications here, we're not going to worry about it. That concludes the lecture.